Hey everyone, welcome back to 102 CD, 102 CEN. We're now on topic number 6. So, we're going to introduce you to these bad boys, which are capacitors. So, we've talked about resistors so far, exclusively for the first 5 topics. But now, we're going to start looking at energy storage components, not just energy dissipators. So, capacitors and inductors are energy storage components, and we're going to look at them from a DC context now, and then in topic 10 we're going to start looking at them from an AC perspective to see how these things work. So, what are we going to do? So we're looking at chapters 6 and 8 today. So one chapter will cover capacitors, one chapter covers inductors. So we're going to look at these, and we're going to look at some basic charging elements, and then that will carry on into topic number 7, which is all about the energy charging, discharging equations, like so. Okay, so what is a capacitor? So in this device, this is a non-electrolytic component, which means you can put it in either way around. There are other ones which are electrolytic, but unfortunately I don't have any of those to hand. They come in obviously different sizes. So this one is a 680 nanofarad, and this is a 220 nanofarad. So note the differences in size, and you can get lots of different ones of these, like so. Okay, so what happens in a capacitor? Well, you've got, as you can see here, you've got 2 conductive plates. So you've got conductive plate there, you've got a certain cross-sectional area A, you've got a certain distance between the plates D, and between that you've got a dielectric material. Now this can be either air, or it could be something else. So it could be some other dielectric material to aid in the energy storage. And the energy between the 2 fields, you've got an electrical field between the 2. So the energy stored in a capacitor is charged in an electric field, whereas for an inductor it's stored in a magnetic field. So that's the differences between a capacitor and an inductor. Okay? And you have a voltage, say VC, voltage across the capacitor between the 2. So what is the energy stored? The energy stored on a capacitor, so as you can see here and here, you've got charge building up on the 2 plates, which is what gives you your electrical field going between the 2. So the Q is the size of a charge on each plate, and VC is the voltage drop across the capacitor. So the charge Q is equal to the capacitance of the capacitor, and aka how much energy it can store, times the voltage across the capacitor as well. And the proportionality C is the capacitance of the device. So again, you can have a small gap, you can have a large gap, you can have a small area of a plate, you can have a large area of a plate. Each of them gives you a different capacitance of the device. And again, when you factor in the dielectric constant as well, that adds an extra layer to it as well. They can also come in different shapes and sizes. So I remember when I was a student, we had to design a spherical capacitor as part of our electromagnetics module. Now the electromagnetics for this first year is included more or less in this module. Okay, but I'm not going to get you to design a spherical capacitor or anything like that. Okay, so different types. So this was the one that we showed you before. So it was a silver mica one, ranging from about 10 picofarads to about 0.001 microfarads. It's a non-polarized device, as I said, so you can put it around either way, and it's used in things like oscilloscopes. This is, so that's a silver mica. Going across here, this is a common one that you'll use in the lab. So these are 2 electrolytic capacitors. So these you have to put the correct way around. If you put them the wrong way around, they'll go boom. So you don't want to put them in the wrong way around. Make sure that there's a little sign on one leg which has a negative symbol on it. So that's the side that you put towards the negative. Okay. And these can range from about 0.1 microfarads to about 15,000 microfarads, and can take voltages like with the silver Maya, from about 5 volts to about 450 volts. These ones are ceramic, so these are ceramic ones. These range from about 10 picofarads to about 0.047 microfarads. They have a much higher voltage because the ceramic lets them have a much higher tolerance to electric. So that goes from 100 volts all the way up to 6,000 volts or 6 kilovolts. They're non-polarized, so you can put them in anyway, and they can work on a wide range of temperature variances. You've got diptalium, which go from about 0.047 microfarads to 470 microfarads, and they have a much lower voltage from about 6 volts to about 50 volts. Again, these are polarized, so these you would have to put the correct way around, and they're used for power supply units. You've got surface mount components, so surface mounts they're getting very common nowadays, and they range from about 10 picofarads to about 10 microfarads, about plus or minus 10 volts. So they're designed to be put on the circuit boards that you put in your mobile phones and things like that. You've got mylar paper ones, so there's paper soaked in a specific chemicals rolled up into a tube structure that you would see here. And again, they range from about 0.001 microfarads to about 0.68 microfarads. And again, they're non-polarized, so you can put those whichever way around. And they have a voltage range from about 50 volts to about 600 volts. You've got motor runner ones, which we're not going to touch that much in the module because that links more into the second year electrical engineering 2. So we're not going to go into that much detail. And then the trimmer variable, basically, the variable capacitors. So essentially, you can change the distance between the plates, which will give you a different capacitance on it as well. So you can get variable capacitors. So it's like the capacitor version of a potentiometer. So you can change the capacitance, and they can change from anything from about 10 picofarads to about 600 picofarads, and take anything up from low voltages from 5 volts that you get from a standard battery all the way up to about 100 volts. So yeah, but the main ones we're going to be considering are these ones here. The electrolytic ones are the main ones that you would use in the lab, or the silver mica ones. But looking at that, look at this table, look at the range of the voltages and the size of the capacitance, and then pick the correct capacitor for the task that you wanted to do. The performance of a capacitor is the same. The charging curves and everything are the same no matter what capacitor you use, but just make sure that you have a look at this. I think this is just going through how they're made. So polystyrene, you've got 2 sheets of 4 separated by a thin plastic film, and that's rolled up. So from about 10 picofarads to 1 nanofarad. You've got the ceramic ones, which are alternate layers of metal and ceramic, a few micrometers thick. That's why they have a much higher tolerance to electricity. That's why they're used for up to 6 kilovolts. And then you've got the electrolytic ones, which are sheets of aluminum 4 separated by paper soaked in different conducting electrolytes. So that will give you different dielectric constants. So different constances here between the 2 plates. So this material here can change depending on which electrolyte that you're soaking it in. And then you have an insulator, which is a thin layer of oxide. So that's why they're from about 10 microfarads to about 10 millifarads. So they're the bigger size ones. Like I said, I've already mentioned about polarized, so you need to make sure that you put it wire up the correct way round. Okay, here's a short video by one of the world experts in capacitors. He's not as energetic as me, as you will see. And yeah, so here he is. Have a quick look, and I'll see you in a second.
Capacitors are devices that provide electrical energy storage of 2 types. One where there's 2 conducting surfaces with an insulator between, so that one side, when you apply a voltage to it, it can't get through the insulator, so it piles up a charge at every little atom on both sides, 1 plus and 1 minus, and stores energy. Polypropylene, when it's built in a manner where it's stretched in two sides. It comes out as a film, and then you stretch it both lengthwise and sideways to orient all the molecules in the direction of the surface of the film. Roll up the film and send it into the winding machines that wind it into, with the aluminum foil we are making to make it, to make the capacitors. The other one was stored energy with a similar thing, except the insulator level is the metal oxide. The insulating film is deposited by anodizing aluminum, and you get very high capacitor levels with electrolytic capacitors. So both tantalum oxide and aluminum oxide are very good preventers from electrons escaping their surfaces. That's what a capacitor is. It's a storage of electric charge.
Okay, so like I said, not as energetic as me, but some very useful information there, so you can rewind that and watch it again if you wish to. So, one of the benefits of a capacitor. So, they're used in many applications, so they're used in everything from your mobile phones to the laptop I'm recording this on. They're very useful. So, they have several important properties. So, the first is the voltage across it can't change instantaneously because the charge has to build up on the plate. So it can't just change like that. It has to change gradually, which is why we get the capacitor charging curves that we're going to discuss, touch on in topic 6 and go on into the next video. They're able to store electrical energy in the electric field, as I already said, and the capacitors vary their opposition to current flow depending on frequency. So that last point is what allows us to build things like filters, so that you can filter out certain frequencies of signals, because its effective impedance, as we call it, will change depending on what the frequency is. And we'll start touching on that in topic number 10. Okay, so topic 9 will introduce the complex numbers and the phases and vectors that we need. Then topic 10 and 11 will go through how to do calculations with an RLC circuit in an AC context, and then that will lead into topic 12, where we actually look at filter design and using the filter design toolbox in MATLAB. So I'm going to actually show you and give you a demo of that in that video as well. So yeah, but that's the important aspect. But obviously from a DC perspective, we're using it as an energy storage discharging system. Okay, so a capacitor can be charged up as shown by this simple circuit here. So as I said in the last video, topic 5, that's where we can use Thevenin equivalent circuits, because you can see here, if you've got a big circuit connected to it, and you want to find the storage, so you've got your one voltage supply, one current, one resistor to find the RC time constant. So you've got the resistor value and the capacitor value. So that's why that is so useful. So in an exam question, it might actually combine Thevenin equivalent circuits with capacitor charging as well. So it's an interesting situation to look at. So assuming in this situation here, this capacitor here is initially discharged. So there's no charge on that plate. And then you've got a switch J1. So when you switch that closed and you press the button, it goes bang, the current can then flow because now you've got a complete circuit. So the current's going to flow around in this direction here, and it will flow so that a positive charge will build up on plate A, shown here, and an identical positive charge is removed from plate B, leaving it with an effective negative charge. Okay, and when the voltage across the capacitor, so VC, when that equals the voltage of the supply, in this case V1, then the voltages will be equal, which means you'll have no potential difference anymore, which means that no current will flow. So if you look at this very crude approximation of a graph here, you've got your voltage on your y-axis, you've got your time on your x-axis, and you've got an exponential curve which would charge up like that. So, and that would show you the charge. And by using the value of a resistor and the value for the capacitor in what we call the RC time constant, that will then tell you how long it will take to charge that particular capacitor. That's why the Thevenin equivalent circuit is so important, because it helps you determine that if you have a more complicated circuit connected to a capacitor. So here's an important slide. So this gives you the charging and the discharging times. So you can see here, here's your charging equation. So you got y is equal to 1 minus the exponent of minus t over tau. And this image was taken from Circuit Analysis Chapter 10 from Boylsted, so I've not actually drawn this myself, so I've properly referenced that. And then this here is your discharging curve, which is y is equal to e to the minus t over tau. So this tau value is your RC time constant. So your R and your C. So one time constant here gets you to about 63% of the saturation value of a capacitor. So this gives you about 63% of its value. If you go to 4 time constants, that pretty much gets you to the full saturation value. So 4 values of a time constant is just short of the full saturation voltage, when the voltage supply will equal the voltage across the capacitor and the current will stop flowing. With the discharging curve, 1 time constant gets you to about 37% of, so it drops from 100% to 37% of the saturation voltage. And again, in this case, about 5 time constants will let you fully discharge the capacitor. So remember the equations. So for the charging equation, y is equal to 1 minus e to the minus t over tau. Remember, tau is your time constant. And for your discharging curve, y is equal to the exponent of minus t over tau. So the only difference is one has a 1 minus and one doesn't. So remember which ones they are, because these won't be given to you. You'll have to remember them. You do get an equation sheet, but not everything is included on there. So yeah, if further components are connected to the capacitor, then the voltage across it can reduce and the capacitor can be discharging. So a capacitor can be charging or discharging. This is an important point, which is why it's in capitals here. So the current only flows whilst the capacitor voltage is changing. Because obviously if the voltage capacitance is the same as the supply, then no current flows because there's no potential difference. So only current flows when the capacitor is either charging or discharging. Okay, so the voltage VCT is changing, so essentially you can say dVc of t by dt is not equal to 0. So we expect current flow is proportional to this change in voltage, so dVc by dt. This is why if you need to look at this, have a look at, I'm not going to get you to do any calculation of differentiations or things like that, or integrations in this bit, but it's useful to know for maths. And again, the maths book that we've got here. So again, your engineering mathematics textbook by K.A. Stroud is again another really good text that you can use to help you with your differentiations and integrations if you want to delve more into the mathematics behind this. Okay, so this is why I said the maths is important. I'm just showing you where this comes from. You don't have to derive these in an exam. You'll just need to know how to use it. So at level 1, you know how to use something. Level 2, you expect to know some knowledge of how it comes from and a bit of explanation about why. And then by the time you get to your final, you should be able to explain things in detail and do the derivations and prove mathematically where things come from. So I'm just giving you this as a point of reference. I don't just like saying, ta-da, here's an equation, go away and use it. I want you to actually know where things actually come from. Okay, so here, obviously, if you've got current flowing, you've got a change of charge. So it's a flow of charge. So this Q, QT, and that equals to C, VCT. So the charge is equal to the capacitance by the voltage across the capacitor with respect to time as well. So if we do the change of charge with respect to dt, so dQt by dt, which is equal to your current, I of t, the capacitance value isn't going to change because it's always going to, unless it's a variable capacitor, in which case you're not going to really move it during operation anyway, you'll set it first. That capacitance is going to be fixed, which means that's why we can take this out here. So we end up with C dv ct by dt. Or if you put it in integral form, you have 1 over c by the integral of I of t dt, which is equal to vc. But this is the main equation that you would use here. Just another example of the graph that we were showing you earlier. So this shows that the current leads the voltage in capacitors. So here, as your voltage charges up to saturation voltage here, the current starts off flowing very high, and that goes in a decaying exponential there. So as the current charges up on a growth exponential, the current decreases with a decaying exponential. So there's your voltage, there's your current. And as I said here, the current leads the voltage, okay? So this is an important term because this will come into play when you're doing your AC systems as well. So if I just get this pen, and some of you might have seen this, some of you might not, but I've wrote civil there. So C-I-V-I-L, civil. And I'm not talking about Captain America Civil War. So you've got your C, so that stands for your capacitor, and it's IV, which means the current leads the voltage. So there's a phase shift that happens when you have a capacitor or an inductor in play. So in a capacitor, it's C, you've got IV, so current leads the voltage. For the L, that's your inductor, you've got VI. So an inductor, the voltage leads the current. So civil, a very useful acronym. Okay, and we're going to cover more about that when we do the AC systems, because when you've got an AC system as well, the phase shifts are more important, because then you need to calculate what these phase shifts are, and that's what we'll do in topics 9 to 11. Okay, but yeah, civil is a very, very useful acronym. So remember it. Okay, so here's a basic multisim system that I built. It's a bit old because it was on the previous version of multisim, so that's why this looks a bit, it's not as graphically good as the others. But essentially with a switch here in the circuit, you've got a single pole double throw switch. So you've got one switch that can switch between these 2 points here. So in this current format here, the capacitor is connected through the resistor down to ground. So in the way it's configured now, that capacitor would discharge down to ground. If the switch was flipped, so it was connected to here, then it would be connected to the battery. Battery would flow, it would go through here, through R, and into the capacitor, and then back down to ground. So then the capacitor would charge up. So in this situation, it would discharge. If it's connected to this point here, it would charge. And we've got an oscilloscope in there, so we can measure and show what's happening. That's the oscilloscope. You can tell it's in Windows XP format. So the variable capacitor allows us to change the time constant, as I said, because T is equal to RC. So you can see there, it's exactly the same as a potentiometer, but so it's got the arrow through it, which represents it's a variable capacitor. So basically, I've just done a simulation here. So I've adjusted the capacitor in the circuit to give a time constant of approximately 10 seconds. And then I've run the simulation and I've alternated between the switch. So this is when the switch is on, when the switch is off in this yellowy line. And the red shows you the voltage across the capacitor. So there you can see it's discharging, it's charging, it's discharging, charging. So you can see that there, and I've obviously not let it get to complete saturation or completely discharged. I've kept it oscillating between the two values, and you can do that as well. But that just shows you about how the capacitor charges and discharges. And again, you've got your multisim software. It's available on Mylon, so you can simulate it. In the video that I did for the introduction to multisim, it actually shows you how to actually build a circuit in there, so it shows you all the components are, so you can have a go at doing that yourself. Okay, so what happens if we have resistors in series or parallel? This isn't only important for the DC aspect, but also for the AC aspect as well. So, assuming the voltage across the capacitors in parallel, so we know the voltage is going to be the same across parallel branches, so there's a parallel combination of C1 and C2, and V, so you've got Q1 is equal to C1 V, and Q2 across here is equal to C2 V. So as we said, voltage is the same across parallel branches, so that stays the same, but obviously the charge is going to be different because you're going to have your current division there. So we expect the equivalent charge is equal to Q1 plus Q2 if we combine those together. So our Q equivalent is equal to C1V plus C2V. So you can basically add these up. So it's C1 plus C2V, which is equal to C equivalent, which essentially shows us that if we have two capacitors in parallel, we simply add them together. So a C equivalent will be C1 plus C2. So it's the opposite of the way resistors work. Because if we have two parallel resistors, you would use the R2, R1 over R1 plus R2 system here. So R1, R2 over R1 plus R2. That would be how we find resistors in parallel. But in capacitors in parallel, you just add them. So it's C1 plus C2. So remember the differences between capacitors and inductors. Okay, capacitors, inductors, and resistors for that matter. And we're going to come on to inductors in a short while. The next logical question is what happens with capacitors in series, and you can probably guess what happens here. So here we have two capacitors that are in series. For the capacitor in series, the charge has to be the same because the current flowing through them is the same. So using our voltage, using the equation from earlier on, we have V is equal to Q over C. So therefore V is equal to Q over C1 plus Q over C2. Now that charge is going to be the same because we're in series. So obviously there's no other charges. So the charge flowing through here, which is the current, will be the same. So we can take this charge and take it outside. We can take this charge and put it outside the bracket. So we have Q times C1 over C1 plus 1 over C2. So therefore our C equivalent would be Q times 1 over C equivalent. So essentially 1 over C equivalent is equal to 1 over C1 plus 1 over C2, which is the same as resistors in parallel. Okay, so the rule is that if you have a capacitor in parallel, it's like resistors in series, and if you have the capacitors in series, it's like resistors in parallel. And you can use the same rules as well. So you can have use for 1 over C equivalent equals 1 over C1 plus 1 over C2, or you could, like with the resistors, you could do C1 C2 over C1 plus C2 is equal to C equivalent. Okay, so remember the differences between the two. Here's an exercise for you to have a go at. So you've got three capacitors, you know what the voltage is, so tell me what the total capacitance is, the charge stored, and the charge on each capacitor. So have a go at that, and I'll give you the answers in the lecture. Okay, here's another circuit, so here's exercise 2. So again, this is just to test your combining your capacitors together. So just remember the rules we said, have a go at that and see if you can tell me what the equivalent capacitance of that combination is. Okay, so let's move on to inductors. So here in the picture is an inductor. So essentially it is a massive coil of wire. And as we know from, and here is so here's your coil, and here is an iron core. So going back to our basic A11 and GCSE, we know that if we have an iron core, we have a coil wrapped around it, we get a magnetic field. So that's why in an inductor, the energy is stored in a magnetic field. So a capacitor is an electric field, and an inductor is a magnetic field. So note the differences. Okay. So for an inductor, there's only voltage across it when the current is changing. So in a DC application, we don't use inductors for anything in DC. So they act as a short circuit. So they don't do anything in DC. But I'm still going to introduce the basics of them here, so that when we come to topic number 10, you actually know a bit about these. And here's the symbol here. So it's represented either by that, or it could be a coil of wire. So the relationship between the change in the current and the change in the voltage was discovered by Michael Faraday. And so the voltage across the inductor VL with respect to time is equal to the value of the inductor times the change in the current with respect to the change in time. So this di by dt proves what this says here, that you only get a voltage if the current is changing. So therefore the voltage is proportional to the rate of change of current. So if I is increasing, then the voltage rises to oppose that change in the current. Okay, so here are several different types of inductor. So these are your common type. They're single inductors, wire wound type. So these are the basic inductors. They have small transmission losses, they have low resistances, and they're used for large current handling capacitors and high accuracy tolerances. So like that. So you've got Mr. Inductor here. You've got the multi-layered type. So these are developed for high frequency applications. You've got ceramic glass inductors, and they're used for as I said, used for high frequency applications, so things like terahertz, gigahertz applications. And you can see here that essentially you've got lots of different slices and they're stacked on top of each other. You've got the power inductors, so these are the wire round types. So these have been developed for the power industry, and they're used about a V-shaped ferrocore, so on a V-shape, not just a normal one, but more like a V-shape. Okay, so you've got your wire round core, you've got your drum, and then you've got your external electrodes connected to them. So you'll touch more about those if you go more into the power electronics aspect of the field. And then the last one is you've got noise suppression components, so you've got film ones. So these are made for thin electronic devices, and as you can see, they're being used in nanotechnology, and other versions are being used for things like RFID, radio frequency identification tasks as well. So there are things like in Tesco, if you've not had your thing deactivated, it will set the alarm off when you go out. So those are the different types, but the main ones that we focus on in this module is this one, as I've said. Again, so what happens if you have multiple inductors in series or parallel? So for an inductor in series, then you got an L1 and an L2. So you got L1 di by dt plus L2 di by dt, because obviously you're going to have an AC current flowing through that. So obviously the L1 and the L2 can be taken out because the di by dt is the same. So we can write that as L1 plus L2 di by dt is equal to V. So therefore, your L equivalent is essentially L1 plus L2. So it behaves exactly the same way as resistors do. So inductors behave the same way as resistors. Capacitors behave the opposite way to resistors when you're combining them together. So therefore, it follows that if you had them in parallel, it would be 1 over L equivalent is equal to 1 over L1 plus 1 over L2, etc., etc., or the L1 L2 over L1 plus L2 that we had previously. So that's important to know, because you will need this for the mandatory question that you have in section A, because that will be an RLC AC question. Okay, similar to the question 4 on the past papers that are online before the new format came in. Okay, so remember this. Okay, so just some voltage current relationships. This also goes back to our civil expression as well that I mentioned earlier. So all of these three are passive components, and the relationship between V and I in each case is using a passive connection. So for the resistor, it's simply V equals IR. So that's for your resistor, which is shown here. For your inductor, your voltage across the inductor is the via of the inductor L times the change in the current with respect to the change in time, because as we said, it's a short circuit in DC. And then for the capacitor, I is equal to the capacitance times the change in the voltage by the change in time, because current only flows when the voltage is changing. So that's what happens in capacitors. Here's an exercise, so have a quick go at that. Try combining all these inductances into one single inductance, and we'll go through that in the lecture. Okay, and that's it for today. Hope you found that interesting. It's a bit of a shorter video than topic 5 was, but that was quite a big topic. So if you have any questions, please put them in the hot question facility so I can answer them in the lecture. And take care. Have a good night, guys. And I'll see you soon for video 7, when we'll be looking at more details about the charging and discharging and the different situations that they are encountered in. Take care and see you soon. Bye-bye.